So, welcome students to the next class of Introduction to Nonlinear Optics and its application. So, in the previous class we started cell phase modulation and try to find out the corresponding equation for cell phase modulation, and from this equation we have a solution, and when we solve that thing we find that amplitude is not going to change for cell phase modulation. Only thing that will change is the corresponding phase. That means, if I launch an electric field in a medium where car nonlinearity is there, what happened that its phase will going to modulate by itself, and this phenomena is called the cell phase modulation. So, today we will going to extend this phenomena or the discussion of this phenomena, and we find out the corresponding frequency shift. Since the phase is changing, so what happened, some frequency shifting will be there, and how this frequency shifting will take place because of this Carr effect we will going to discuss in today's class. Well, let us go back to our old equation. So, we have the expression of cell phase modulation, this dE1 dz is I 3 divided by 8 chi 3 omega divided by C n1. If I write this 3 8 chi 3 omega divided by C n1, then we have a straightforward, if I define this as a gamma, we have a straightforward expression which is del E1 del Gz is I gamma mod of E1 square E1. This is the expression that we have. This is the differential equation for cell phase modulation. Well, once we have the cell phase modulation equation in our hand, the next thing is to show that the power will remain conserved. So, E1 will going to evolve over the distance, but is there any change in power, and that will going to shift. So, here we can find that in this expression everything is related to E1. So, that means there is no power exchange kind of term may not be there, but in order to ensure these things, let us find out how the power will going to evolve. So, power is clearly proportional to mod of E1 square. Power P1 is related to the power of electric field defined by E1. So, if I try to find out the derivative of mod of E1 square, so d dz of mod of E1 square is E1 d1 star z plus E1 star d1 z. So, E1 star dz I can find from this equation. So, what should be the del E1 star dz? It should be simply the complex conjugate of this quantity, and the complex conjugate means there should be a negative sign minus I gamma mod of E1 square not going to change, E1 become E1 star. Now, these things will be multiplied by E1. So, eventually we will have minus of I gamma mod of E1 to the power 4, because this term will be multiplied by another E1 star. The entire thing will be star, this thing will be star, and then it will be multiplied by. So, we will have a minus of I gamma mod of E1 square E1 star, and then another E1 will be multiplied with these things. So, when we have another E1 multiplication, so we will have E1 to the power 4 mod of E1 to the power 4. In a similar way, the next term will be simply plus I gamma E1 to the power mod of E1 to the power 4. If I add these two things, we will have 0. So, that means E1 is constant, so P1 is constant. So, there is no change of power, and E1, which is a complex amplitude, E1 which is complex amplitude and can be defined as mod of E1 plus some phase. So, this differential equation suggests that this amplitude part will not be a function of z. So, only the phase term will be function of z. So, only the phase will going to change. In the previous class we basically find out the same thing, that the phase is going to change, and that is why it is called the self phase modulation. Well, amplitude is now conserved. Once the amplitude is conserved, as I mentioned in the previous slide, that E1 can be represented as mod of E1 into the power I phi. So, now if I represent this E into amplitude and phase term, and then if I make a derivative over that, then I can write this derivative as E1 e to the power I phi. If I divide this derivative, we will have d E1 dz e to the power I phi and I Ei e to the power I phi d phi dz. But we know that di dz Ei mod of Ei is not a function, it is a constant, so not a function of z. So, this term will be 0. Since this term will be 0, we will have d of Ei dz is simply equal to I of mod of Ei e to the power I phi and then d phi dz. Di dz is again according to our equation is equal to I of gamma of mod of Ei square E1. So, we will have an differential equation of phi. From this, what we are having is the differential equation of phi. So, differential equation of phi will be simply this. So, phi is changing. So, how the phi is changing is the thing that we are trying to find out, and we find that d phi, finally we find that d phi dz, phi supposed to be a function of z, is simply equals to gamma E1 square. Well, if I integrate these things, because E1 is not a function of z, so we can readily integrate this. If I integrate these things, we will find that phi, which is the phase of the electric field amplitude, will now linearly changing, and it will be a linear function of z, and the solution is simply gamma mod of E1 square z. So, if I integrate, we can put this phi 0, so that there is a reference frequency, reference phase, that at z equal to 0, if there any phase, we can write phi 0, but if I say this is equal to 0, so phi z is simply function of z and will change linearly as shown here in this figure. So, we have expression of E and phi both, and we find that for self phase modulation the amplitude is not changing, but the phase is changing, and the change of phase is linear in nature. Well, this thing we have already, this solution we have already figured out in our previous class. Once again, to remind these things, that how the phase is changing, in order to understand this phenomena in a different way, we again show these things. So, this is the equation, this is the total equation of the electric field, and this total equation of the electric field should contain both the equation of phi, because this is a complex equation. E is now having two parts. One is mod of E, if I write this E1, mod of E1 is the amplitude part, and one is the phase part. So, one way is to do this problem by putting amplitude and phase part and separate it out, and then find out the solution of E1 and phi, that we have done in the previous way, or you can directly find out E1 and put it here, and once you find out E1 and put these things, you will find that E1 is now having E1 0, the amplitude part, and the phase part, the solution part directly. So, in the previous calculation, we separately find out the solution of phi by solving these two equations. One equation is simply d1 dz is equal to 0, that was one equation, this amplitude equation, and phase equation was d phi dz is equal to I into I in terms of gamma, it was just gamma. So, let me go back and check, it is only gamma mod of E1 square, because inside the gamma all this N2 and all these things were captured. But if I write this term into these things together, then we will have a solution, and this solution suggests that there is a the field will going to change, because the propagation constant k prime is now changed because of this nonlinear effect. So, this solution we have already done. So, just once again show that you can do that in this way also. Now, the phase change can also be figured out, and since we have a solution in our hand for phase, we can directly do that in terms of gamma, but here the phase change one can calculate, because E1 omega is half of E1 e to the power I k z omega, which in terms of phase I can write as half of E1 e to the power I phi. Phi is k1 z omega t. With SPM, this is without SPM, the way one can write the total electric field. With SPM, one can again write same electric field, but only change is here is k prime, because k will be k1 was the propagation constant without any kind of nonlinearity, and k is the propagation constant of the system with nonlinearity. So, if I write k1 z minus omega t as phi nonlinear, because this is coming because of this nonlinear effect, then phi nonlinear is this quantity. So, phi was the phase without any nonlinearity, and phi nonlinear is a phase with nonlinearity. Now, if I try to find out what is the difference between these two, so we will simply find that the difference between these two phase is simply N2 K0 intensity into Z. Now, all this, the facility to find this form of phi 2 is we can readily find out for a given intensity what should be the change of the phase. So, now N2 K0 I Z all this value one can obtain, and here is the example that what should be the phase shift, nonlinear phase shift, if these values are given. So, the value that are given is N2, which is 3 into 10 to the power minus 20 meter per watt. The value of P is given as 1 watt, A is given at 100 micromillimeter square. Previously, if you remember, in one calculation we consider 100 millimeter square, now it is micromillimeter square, it is very small. So, 10 to the power minus 10 meter square is the area. So, intensity with this area and power comes out to be 10 to the power 10 watt per meter square. The operating wavelength is given as 1 micrometer, which is 10 to the power, this quantity is 10 to the power of minus 6 of meter. Length, here it is a jet. So, over the distance this phase will going to increase, the change of phase will going to increase. So, we say it is around 20 kilometer. So, delta n, the change of refractive index for this, if we calculate it is simply N2I. So, N2I is now 3 into 10 to the power 10. Now, what should be the phase change? The phase change will be delta n N2K or simply N2K0I into Z. So, delta n multiplied by k into 2 pi divided by lambda 0, because k0 is 2 pi by lambda 0. So, delta n is 3 into 10 to the power minus 10. Why it is delta n? Because delta n is nothing but N2I. So, just if I replace N2I to delta n, so delta n L k0. So, k0 is 2 pi by lambda 0. So, delta phi simply becomes 3 into 10 to the power minus 10, which is this value, multiplied by 2 pi divided by 10 to the power 6, the value of 2 pi by lambda, and then length 20 kilometer, 20 into 10 to the power 3. So, if I calculate all these things, then the final expression that we have is delta phi. The change of phase is around 12 pi, which is a good amount, That means, if a pulse is launched due to this nonlinear refractive index, what happened that the phase will going to modify and phase is going to change, and the phase will change around 12 pi after a distance of 20 kilometer. So, if I go with the nonlinear fiber with 20 kilometer, the phase will change around 12 pi for this given set of parameters. Okay. Now, another important thing, and that is the instantaneous frequency. So, instantaneous frequency is a nonlinear phase divided by the time with a negative sign. So, this is the expression of the instantaneous frequency. Since the nonlinear phase phi nonlinear is containing the intensity, so now it is important to know that this intensity is function of t. So, that means, the value of instantaneous frequency can be a function of time. So, normally what happened, let me write here. So, normally phase phi is given as k z minus omega t. So, if I write d phi dt with a negative sign, in the right hand side we simply have omega. This is the frequency of a system, this is the frequency of a plane wave that is moving. Now, our expression is slightly changed, because we now have nonlinear phase, and in nonlinear phase what extra term we have? We have, instead of k, we have k prime z minus omega t. What is k prime? K prime is k0 z plus n2 of z of n2 z and then I, it is something like this. So, what is k prime? We already defined in the previous slide. So, let us check what is k prime. So, k prime is simply k1 n2 k0 I. So, k1 is the propagation constant corresponding to the refractive index n1. So, now what happened, because of this k prime, if I now put this entire equation, so phi nonlinear again is k prime z minus omega t. So, when I make a derivative of these things to find out the instantaneous frequency, nonlinear dt, so we will have minus of these things is plus of omega, the derivative of this quantity, plus z multiplied by dk1 k prime and dz. So, dk prime dz is this quantity. So, that means the intensity is involved here, and we know that intensity can be a function of time. If intensity is a function of time and if it is Gaussian in nature, then we can have the instantaneous frequency in our hand. So, this is the expression of a plane wave moving with the frequency omega, and this is a Gaussian field. So, now we have an electric field with Gaussian distribution. So, this is a distribution of a Gaussian electric field with frequency component omega. If I plot the real part of these things, we will have this kind of structure. Intensity will be mod of square of these things proportional to. So, I0 of this, so distribution of the intensity will be something like this. it will be again a Gaussian. And now if I make a time derivative of this intensity, we will have a term like this, which is the derivative of a Gaussian function. So, we know that if I make a derivative of Gaussian function and plot that, it will be something like this. So, instantaneous frequency is now omega 0 plus this quantity. So, that means if this is a distribution over time. So, if I go over the time, the distribution of the frequency which is uniform here will not remain uniform because of this additional term. And this is why, because in our system we have a refractive index which is now function of time also, because the intensity is a function of the refractive index is a function of intensity, and now intensity is a function of time. Well, if I now use these things, if I now use this expression as I mentioned, then we can plot this together, and if I plot this together, we find the instantaneous frequency is now having change. This quantity is changing, so that the instantaneous frequency has to change, and this is some sort of modulation that is over the frequency omega 0. So, omega 0 is the frequency shown in here, and what happened that in the left side this quantity will add up, and then at the center it will not going to change, and then it goes to the negative direction. So, if I look these things qualitatively, then we find that this is the uniform distribution of the frequency. Because of this Gaussian distribution of the intensity, what happened, the instantaneous frequency is now function of time. So, if I go these things, it is a function of time. So, first part of the intensity, first part of the frequencies now will be chopped or confined more. So, here the frequency is increased. So, we will have something omega plus delta omega, which is the addition of this quantity. And then what happened, here we have some frequency reduction. So, some frequency will reduce this part because we have a negative portion in this region. So, one portion of the pulse will be blue shifted, and another portion of the pulse will be red shifted because of this typical distribution of intensity, or the derivative of the intensity rather. So, this kind of pulse is called a chopped pulse. So, one very important consequence is that when the light is propagating through a medium, and if the medium is nonlinear in nature and Carr effect is there, so what happened, that is phase will going to modulate. Not only that, the frequency component is also going to change. Some different frequency component will appear because of this distribution of intensity or the derivative of this intensity. Well, if I now try to find out what is the frequency change of that, we can readily find out. This I can give you as an homework, but all the problems are done here, but I ask you to do that by your own. We will discuss this anyway in this class, but I will not going to discuss in detail. I just give you the overview of the problem, and I ask the student to please do this problem by your own. So, the problem is what should be the maximum change of the intensity. So, if I go back to this figure, then I say that here the frequency is going to be changed. So, here what happened, that I change the frequency, this is the, so we have a frequency here omega. So, on top of that we have a modulation. So, some portion of the frequency will be added up, some portion of the frequency will be subtracted. So, if you can see that this is a gradual change altogether. So, there should be some value for which we have the maximum change of frequency omega plus delta omega, this is the maximum change, and there is a maximum deviation or maximum reduction of the intensity also in this particular point. So, the question is, if the distribution is Gaussian, what should be the maximum change of the frequency? What should be the maximum change of the frequency? Well, the result is already shown here in this slide. If you look this slide carefully, I calculate these maximum value of the instantaneous frequency. So, the maximum value of the instantaneous frequency will be simply the maxima of this term which is sitting over here, and if I calculate the maxima of this function by making the double derivative of that and making it 0, then we have the value of t at which it will be maxima. Next thing is just need to put this value of t here, and eventually you will have delta omega, which is the change, maximum frequency change, which is having a form like this. Once we have this form, the next question will be asked that what should be the corresponding frequency, corresponding wavelength shift, because wavelength, that means if I launch a particular wavelength lambda, it will going to shift. So, what should be the shift of the wavelength due to this intensity distribution, temporal distribution of this intensity, which is Gaussian in the form. So, these are the value that is given, and if you put this value and do all this calculation, you need to use this expression which is here, and once you do that, you will find for the given value the change of the frequency or the wavelength is 6 nanometer. So, 6 nanometer wavelength will shift because of this, which is not that much, but we can increase this radically if I increase the amount of power or if I reduce the corresponding area. So, if I reduce the area, the value of the nonlinear effect will increase radically, and this value can change up to many nanometers. But anyway, for the given values you will find that this will be around 6 nanometer. So, with this note, let me finalize today's class. So, two important things we note to this Carr effect, and that is very important. This concept you should understand very clearly, that this is my Carr effect, and in the Carr effect we have intensity in my hand, and this intensity is the function of position as well as there is a temporal part of the intensity. So, when we say that the laser light is falling over some place, so it is illuminated over a space, and this is the distribution, is the spatial distribution. Due to the spatial distribution, what happened, that we have a self focusing kind of effect, but also the intensity has some distribution in temporal domain. So, when the intensity is temporal domain, what happened, that we have the phase modulation of light. So, light will be modulated, and this two kind of modulation is there. In one case it will be a self focusing when you consider the intensity is distributed over space, and if the intensity is distributed over time, then another phenomena will be there, and this phenomena is the chirping of the pulse or the shifting of the frequency. This is called the nonlinear shift of the frequency or the self phase modulation in other term. So, this will appear when the intensity is a function of time. So, with this note, I would like to conclude the class here. In the next class we will discuss more about other issues. So, thank you for your attention and see you in the next class.